Hello, you hear me?
Yep.
Alrighty.
How's it going?
Doing fine.
Huh?
Doing fine, I guess. Yeah.
Awesome.
I'm taking my second full length tomorrow. So, the blueprint full length. I did want to ask for those full lengths, when you say blind review, just to make sure, I have to go over every incorrect problem without seeing the answer and try to get it correct the second time.
So, so you look at the questions that you got wrong. So, like, let's say that you finished the section and you got like 10 questions wrong, and so what I want you to do is uh write down which of those 10 questions you um
Around.
yep.
And then what do you want me to do after that?
Oh yeah,
Redo
sorry.
them?
So yeah, you look at the questions that you got wrong, after you finish your test, just write down on a piece of paper, like, which passages those are. Uh, but this time, without looking at the answer, just do the questions that you got wrong the first time around. And this time without a time constraint, because that's the entire reason for the blind review. It's to separate the questions that you got wrong because you really didn't understand it from the questions that you got wrong because you're running out of time. So the blind review just involves you doing the questions that you got wrong without the time constraint.
Okay. Um, and do it for all sections, including cars.
Yep. Yeah.
Okay.
But it's going to be just the incorrect questions. Yeah.
Yeah. Okay. Uh, and and that'll be on the second day. So like for each full length, you should have a total of 2 days, one for doing it, and the second day should be reviewing and blind review.
Yep.
Okay. Um, sounds good. Okay, today, uh, I wanted to go over two different things.
Yeah.
Um, and I also do prefer that like we try our best since it's 2 hours, like it's two main topics. So like the first hour for one topic and the second hour for the other. Let me share my screen. Are you able to see it?
Yep.
Okay, so this first, so I guess for the first hour, I just wanted to go over acids, bases. Um, no matter how many times I try to get better at this topic, I just can't seem to. Um, and the main thing I wanted to go like ask you, I guess, for help is just pH, pKa, maybe like in the explanation here, they show like an ice table, but I wanted to see how you do I guess these problems.
Uh,
Um
so what can you tell me about acid and bases? Like what are some of the things that you feel like you understand, or some of the things that you feel like you don't understand?
right, so I understand the relationship between like Lewis bases, Lewis acids, in terms of just electron donors, electron acceptors, and
Okay.
then also like the Bronsted and the Bronsted acids and bases, right? So you have like the Bronsted acid which donates a proton, Bronsted base accepts proton, and then Lewis acid accepts an electron pair, and then so yeah, that I understand.
Mhm.
Um,
And
my main issues,
yep.
sorry, my main issue is calculating like pHs and pKas, when to use like the Henderson-Hasselbalch equation,
Mhm.
stuff like that.
Okay. So what can you tell me about pH? Like what is that really?
Like it's I guess um a logarithmic way of basically saying what's the concentration of protons in a solution. And so the less the pH, the more, you know, proton concentration you have, and likewise for hydroxide ions.
Mhm.
The lower the pOH, the more hydroxide ions.
Okay. So did you get? Oh, so let's see. Um, so is this the only question for this passage that you got wrong?
Okay, so the two questions I got wrong, well, I think this one was a stupid mistake.
Huh?
I think. Like I can differentiate between acid and conjugate base and then base and conjugate acid.
Huh? Oh yeah, just
These
yeah.
these were the two I got wrong. It was calculating the pKa and
Yep.
like pH.
Okay. So I think it would be a good idea then, because if it was like one question for the sake of time, I would just kind of read it myself. But I think having you read it would be a good opportunity to pick up buzzwords. So basically I'm gonna ask you to like read it, and after each sentence, just tell me what you think the buzzwords are, if any.
Okay. Hydrolysis is a process in which a chemical substance decomposes by reacting with water.
All right.
Um,
What's
yep.
There's a buzzword in there. What would it be?
Reacting with water or
Maybe
de hydrolysis. Okay.
right. What can you tell me
Okay.
about hydrolysis?
Um, well, something splits because it interacts with water.
Uh-huh. So um so yeah, if you look at the word, right, hydro means water and lysis is like breaking.
Mhm.
So it's breaking bonds. Um, what's the opposite of hydrolysis?
Condensation.
Uh-huh. How is there another word to describe that?
Um, Hydration.
Well, what happens to the water in when a bond is formed?
When the bond is formed, the water leaves, right?
Mhm.
Um, and then in order to break a bond, you add water.
Yep.
So hydration is probably hydrolysis, right?
Yeah. So if you just
Okay.
take that first word, like if you're really thirsty, what a what might you be?
You're dehydrated.
Yep. So that D part, DE means, it's lost, like it's not there anymore. So
Uh-huh.
that works for the condensation term, which is so the opposite of the hydro would be dehydration, and then the opposite of lysis would be the synthesis. The word synthesis means like combining things into like a larger whole.
Mhm.
So,
Okay.
so yeah. Okay, cool. Yeah, you can continue.
Okay. And the hydrolysis of certain ionic salts, water itself can be decomposed to some extent via an acid-base reaction in which a cation acts as an acid or an anion acts as a base.
Okay.
Um, do I find a buzzword or
I don't think I see one here, but yeah. What I'm
okay.
realizing is what if they're talking about hydrolysis of water, um, you guess you would need an acid or a base. But
Mhm.
yeah, you can continue.
Although metal cations alone have no H plus ions to donate, some cations can be hydrated by forming coordinate bonds with neighboring water molecules in solution, as shown in reaction one.
All right. Now tell me what you see here in the in reaction one.
Um,
Like, what's that M supposed to represent?
the M, a cation, like I mean metal. Sorry.
Yep, both metal cation, right?
Yeah.
Mhm. And then what's happening?
Um. Well. it's reacting with water.
Yep. So this is a special type of bond. So like typically, I mean, like the bond between like, let's say the bond between oxygen and hydrogen is like a covalent bond, which means that it produces a compound that's neutral in terms, well, I should say not neutral, but that doesn't have a charge, right? So the charge for this water molecule is 0, right?
Yep.
And that's just how most things are. Like pretty much most chemical bonds that we see that are drawn with like a line is going to be like a full-fledged covalent charge. But here we have something called a coordination complex.
Mm-hmm.
And have you ever seen anything like that?
Yep.
All right, what can you tell me about it?
What I remember is that I think one example is also like hemoglobin forming like coordination complexes. I saw that.
Mhm.
But it's like where um one thing is fully the one giving the electrons.
Mhm.
That was like a really bad way to word it, but
Yeah, yeah.
um
So so yeah, we essentially see the water molecules, surrounding the metal, but unlike a regular covalent bond in which the overall compound has a neutral charge, um, this has a charge, right? So if it has a charge, like that shows like at least how it's different from a regular covalent bond. But yeah,
okay.
so yeah, so this is just so reaction one. This is a I would say that this would be kind of like a buzzword because it's covering something that is important. And
Mhm.
that's the coordination complex.
Okay. In the resulting complex ion, the central cation shifts electron density away from the H atoms by an inductive effect, making it possible for the complex to donate H plus ions to water molecules in the solution and form H3O plus as shown in reaction 2.
Okay, so I would say here, like the buzzword would be, well, what would you uh say it is?
Okay. I don't know, there's a lot of words. I was gonna say inductive effect. I was gonna say inductive.
Yeah,
Yeah,
so
yeah.
that's like electronegative, the stuff pulling it towards itself. I
Okay.
think much as like 6 carbons, like distance. But yeah, okay. So they're saying um that this complex makes it so that I guess it may result in um more acidity, making it possible for the complex to donate protons to the water molecules in the solution and form hydronium ions. So it seems like that this is behaving like um an acid, a Bronsted-Lowry acid, right?
Mm-hmm.
Yep. Okay, you can continue.
Okay. Um, consequently, aqueous solutions of small, highly charged metal ions are often weakly acidic.
Okay, so
Um, Wait, one thing you said, what is behaving as a Bronsted-Lowry base? You hear me?
Oh, sorry. What'd you say?
Sorry. What did you say is a Bronsted-Lowry base?
Oh yeah, so that definition is probably the one that most people think of when you think of acid base, and it's
Yeah, yeah.
acid donating protons and the base accepting protons.
Right. And so here the Bronsted-Lowry base is the whole this big molecule.
Yeah, yeah. I'm just trying
Okay.
how reaction two is different. I mean, I see that, it's one H2O instead of six, and that it produces hydronium. Um, from I don't know, I guess like there's a loss of a hydrogen as well. Do you see that? Kind of.
Um yeah. Yeah, I see it.
So okay, so yeah, it looks like it's behaving like a Bronsted-Lowry acid here. I don't know how to classify it compared to reaction one. Like I honestly don't really see. Maybe it'll make more sense as we move forward, but I guess okay, inductive effect, and then I guess for these small, highly charged metal ions, where the n great or is greater than or equal to 2 are off. Maybe I'll do like weakly acidic. Yeah. So yeah.
Okay. Um to investigate the properties of zinc and aluminum, a chemist performed the following experiments. A sample of zinc salt was dissolved in water to produce a 0.10 um, molar zinc 2 plus solution.
All right. So okay. Yeah.
Um, the solution was checked with the pH probe, and the measured pH confirmed that the solution was weakly acidic. Uh, and then ZnH2O6 2 plus was found to have a pK of 9, as reported in the scientific literature.
Okay. So let's see. Yeah, what do you think is happening here?
I mean, so after like the zinc salt was dissolved in water,
Mhm.
um, the the, the pH after the reaction was weakly acidic. Um,
So they took this zinc salt, which you know is going to be um like a solid, and they put it in water. We don't know how much water they put it in. If they did tell us how much water they put in, we would be able to, using the molarity that they also give, calculate what if they gave you like some value like 100.
right. So what I do know is like pH plus pOH equals 14, and also Ka times Kb equals 10 to the negative 14. I mean, when they're leaving is 0.10 molar. Um,
It said 100 milliliters.
mhm.
What can both these values help you determine?
The concentration. Um, that's the thing. So like with the zinc salt, like when it's being dissolved, if we're saying that it's weakly acidic, does that mean like the zinc salt was acidic?
Oh, so that's just when we mix, so like after we mix it in water. So essentially, so yeah, the reason I was just saying that if they gave you a volume, I was asking like what would also like given that they give us like the concentration, if we had the concentration and the volume, we can multiply the two to get moles. Okay.
Mm,
But now let me take a look even closely. So the solution was checked with a pH probe and the measured pH confirmed that the solution was weakly acidic. Um, and then they gave us, so okay, it seems like, so zinc would be an example of, I guess the metal here, and it likely will have a bunch of water molecules kind of surrounding it. Um, and that can help it have an acidic effect. But then for some reason, okay, weakly acidic, but a pKa of 9 is kind of, I don't know why it's 9, but because 9 seems like it's higher than what it should be for an acid. Like I guess it's a weak acid, but still, yeah. But yeah, it's gonna be this thing that's acidic. Maybe that.
Okay, so that's the zinc salt, or
So the salt is going to be, well, you're going to add it to water. So the salt form of zinc would not be what's acidic. It would be the zinc cation, because when you dissolve it in water, then you break up the ionic bonds of something. So that's, yeah, so that's what they mean by that.
okay.
Yep. I mean, like it would look like this. The zinc solid would turn into zinc 2 plus aqueous plus the, well, I didn't put the plus H2O here, but let me do that. And then this one would be that.
And okay.
Mhm.
Um, it would be going both ways though, right? Like I know you probably just forgot, but I'm just confirming. Or would it fully?
Oh yeah, sorry. So it's probably going to be, I mean, up here it kind of shows like a longer arrow.
Oh yeah, yeah, yeah. Okay, okay, okay.
I don't know if that means that it is favored in the backward direction or not,
Yeah, yeah.
but yeah.
Okay. I'm just confirming that it's going both directions. Okay. So I guess experiment two. A sample of an aluminum salt was dissolved in water to produce 0.10 molar Al3 plus solution. Solution was observed to turn blue litmus paper red and had a measured pH of 3. The pKa of AlH2O6 3 plus was not found. Yeah, okay.
Okay, so
Making that.
that one's a lot more acidic, right?
Uh-huh.
Um, and also I want to say that if they give you a pKa value, or whenever you're dealing with pKa, you don't necessarily, I mean, sometimes, yeah, you don't necessarily have to use the Henderson-Hasselbalch um equation. So like pKa would be, negative log of Ka, and Ka will be, the concentration of the products over the reactants. So you could even, use the pKa value that they give you to find what concentration of, zinc aqueous exists, and, what concentration of like the number of hydrogen or protons or hydronium ions. So that's just something that you could also see. Or you could also use that to figure stuff out. So, okay, so yeah. Any questions on this so far?
No, I mean that's what you just said is gonna like the main thing I had the issue with. So like in question five, we're gonna have to use like the Ka value to then like set up an equation
Hmm?
where it's like, yeah.
Okay. So let's see. What's the pH of the zinc 2 plus aqueous solution in experiment 1? So yeah, walk me through your thought process for this.
I mean I butchered it. I used Henderson-Hasselbalch here. It was wrong. So I saw the explanation. From what I understand, we first have to like we can I mean I also had an issue before setting up the equation itself. But now that we've set up an equation, I guess we can find the Ka from the given pKa value.
Mm-hmm.
And so the negative log of 9, uh, so it would be the Ka value would be 1 times 10 to the negative 9.
Okay. I think that, let's see. So, okay. All right. When you set up the Henderson-Hasselbalch, what, I guess, what was there any like variable, like, tell me about that? Because I mean, seems like we have a given pKa value for this. We have a given um pH.
Well, I did pH equals 9 plus the log of 0.10.
Mhm.
That's what I did.
Mhm. All right. I think I'm overthinking this, to be honest. So let me think about this. Weakly acidic. I mean, that's what I said at first when I saw the pKa, but I think weakly acidic would mean less than a pH of 7. I think that could work. Wait. Yeah. Okay. Maybe this one.
Wait. Um, yeah, there.
Oh, okay.
Okay, so how'd you do it?
Yeah, so I just I mean eventually, but I just saw that it said weakly acidic and I looked at the choices and I know that set like if it's higher than 7, it's basic. If it's lower than 7, it's acidic. And so that would rule out these two. And then between these, I guess I kind of like not like, well, yeah, maybe I guess.
No, I appreciate the honesty. Um,
But okay, let me see. So this is what I kind of was trying to or thinking about doing.
yeah, their explanation is so complicated, and I was just like, wow.
They're doing it with where the X value is not negligible. So thankfully for us, it would be negligible because we're not, likely to see questions like this on the actual MCAT where, you have the ice table with, or where you actually have to do the ice table. But yeah, but above this, though, if you go up like with that, yeah, this Ka value here, a lot of times that can help because they give us a pKa value of 9, which would be 10 to the power of -9, right?
Okay.
And so then if you can then set this just equal to 10 to the power of -9, you can also you can plug in over here the zinc aqueous um like solution. And H3O plus is going to just be, since we know the pH, or well, I guess that's what we're trying to find here. So okay, that's something that we have to find. So I'm going to use green. So green will be the things that we have. So meaning they give us a pKa of 9, which means that we can know what the Ka is, so we can have that down. We know that the solution is 0.10 molar, so we have that. And then this guy, let's see. Yeah.
But my question is, why are you doing zinc aqueous on the bottom if you put zinc solid on the left side? I know H2O does not even go into this.
Yeah, that's a good question. Okay. All right, so I think that what might happen here is that something like this first happens, where you just put it in water and it forms this coordination compound. But it can also go from there to act as an acid over here. So if this is like the zinc 2 plus, or rather, yeah, like if it's a zinc 2 plus, in that process of all of the water molecules surrounding it, it's going to be this, this coordination complex. But then afterwards, it can then donate a proton because apparently, it's going to be weakly acidic from what they tell us. So I think that that this and this, I mean, they're the same thing, are reactants now. And this, when it's acted as an acid, would be the product. So if this is initially what you have with this, it would eventually turn into this, and then after that, act as an acid to turn into that.
Okay, anyways, so then setting up the equation, what would you get?
Oh yeah, I think it should be the same thing. Oh yeah, so they tell us over here that this is this thing down here, so that's where we put the 0.1. And then lastly, I'm thinking, what would this number be? According to this, it says that they're equal as well, which actually makes sense because in the reactions that we have, or rather in reaction 2, we have, the same coefficient for each thing. So if we have the same coefficient, it means that, there's a 1-to-1 mole ratio. So however many moles of this acid, however many moles of the water, would produce the same amount of total moles for this, hydroxylated coordination complex with the H3O plus. So both of these values should be the same. And if you go down, I think they'll kind of talk about where it can be, yeah, so this like double X or XX thing. Here, I'm just gonna clear what I wrote, but over here, wait. Oh, I thought I saw something, but oh, this part. The double X here is kind of like, I think we may have talked about this briefly before, but it's like when you have solubility, like AX2 would break apart into A plus and 2X minus, something like that. And if it's just AX, it would break apart into A plus plus just 1X minus. And then the last one would be AX3, which would turn into A plus plus 3X minus. So those are the 3 possibilities that you can have when you do this type of question with figuring out, the new concentration of something. So these are just the options that you have. So to show, so like if they're both equal amounts, you would get x squared. If it's this with twice as much of the x, that would be x times in parentheses 2x squared, which is then 4x cubed. Remember that 4x cube thing?
Which one?
Oh, like over here.
Yeah.
Yep. So that's when you have something like this with ax2, where a is like the metal and x is like the non-metal. And then lastly, it's this one where you have x times 3x in parentheses to the third power, which would give you 27x to the fourth power.
Okay.
So if they have the same amount of a plus and x minus, then you can treat like the a plus as, x, and then this one as x. And so that's where they get this from over here, where they have the x times x, because there's going to be equal amounts.
All right.
Mhm.
I mean, I just was confused about how, like, I guess they set up the equation
Mhm.
with like the zinc, um, OH plus, and then there's the zinc on the bottom 2 plus. I mean, yeah, like you explained that, but I was still just
Yeah,
confused.
where it is that you're talking about.
Hmm?
Oh yeah, so show me where.
Yeah. I mean, it's this like this equation. Like I
Mhm.
get that the products over the reactants. Um, so are they just taking this? Like, is the what stuff that's on top like just the products of this
So
over?
yeah, so in reaction one, these are the reactants. This is the product.
Yeah,
Reaction two, the previous product
yeah,
is
yeah.
a reactant.
But the main reaction they're talking about is reaction two, right? When they're talking about like the zinc.
Mm-hmm. Yeah.
Okay. Well, how about this, right? So, like, cause here you're getting the pH but not the pKa. But is it a similar approach?
Oh, this looks exact. Wait, this is not the one that we just did, right?
No.
They're the same.
Yeah.
Okay. Uh, all right. What do they say about this in the passage? Is this? I guess maybe they're talking about the thing that was not in the literature.
Yeah, so this is for experiment two. They're basically testing us just in a different way because here we need to find pKa, not pH.
Got it. Experiment two, we have this amount of this aluminum aqueous and pH of 3, and pKa is of this thing with the 3 plus charge and the 6 aluminums. So essentially, this is going to look just like this, except this middle M is going to be aluminum. And okay, so now this should be something like this. Okay. So I think all right, so this is going to be our reactant here, and the product would be something like this, I think, where you have, so that's where I changed it to say that there's 5 of these water molecules, but there's also an OH group here. Oh, and then this gives us a charge of N minus 1 plus. So if the initial one was 3 plus, this should just be 2 plus. And yeah, and then it'll behave. So this is the so this is where it is the acid. This is where it's the conjugate base, which is then, well, yeah, pretty much that. So conjugate base and then H plus concentration here. So you could, so okay, do you try this with Henderson-Hasselbalch and it wasn't working?
No, it was not.
Okay, so let's see, pH. All right, set it up like that. Something tells me that there could be a more simple way of doing it, but I don't know. Let's just continue. So pH of 3 is equal to, okay, pKa, we don't know, plus log of the I'm gonna just do that to free up some space, but log of, so the A, okay, so this is the HA, this is the A minus, and then this is just the H plus. So the aluminum H2O thing. Okay, and then we can do pKa is equal to 3 minus log of, I'm just gonna write A minus over HA. And that should be, I think it's going to be similar to the previous one where we're going to get an equal amount of conjugate base and the acid, but because in that case then this thing would just be like X. But let's see, maybe I can do the 0.1. Oh crap, oh no, JK, is this 5 again?
I don't think so. Oh, okay, yeah, it is.
Okay. What?
Yeah, so again, they did this whole ice table that like I just refuse to want to do.
Yeah, let me see here to let me see from the top of it. Okay, so they're just writing out the Ka, okay, and then they write out the H3O plus concentration, and then these ones are equal, which we knew, and that would be 0.1, and then this one, let's see, minus 10 to the power of -3. Okay, yeah, okay, that works. And we have this, we have this. Okay, let me take a look underneath. So, okay, so we have this. All right, yeah, I guess it's similar to the previous problem with both like the value of this and this being equal.
Should I just assume from now on when I do these types of problems that like I'll have to set up as like x squared over like
Yeah, yeah, yeah. I would say so. I mean, you're not going to see this like kind of thing, because it's going to be values that are um too small for it to matter, thankfully. But yeah, when you set up this, you want to see, because you have three possibilities where they're both equal, and in which case you'll get x squared, or then one has like 2 moles compared to this other one, and that would be the 4x cubed, and then the last one would be that 27x to the fourth power. But yeah, I guess the takeaway with this is just that when we look at the reaction, we see that the coefficients are all the same. It's 1. So there's a 1-1 mole ratio. And that means that essentially what that means is that it's pretty much like the concentration of your reactant is like the square root of the actual thing. So, but yeah, it's pretty tough, these 2 questions that you showed me. And for this one, yeah, it's so weird that it's pretty much the same thing, but it's going to be the same thing because of equal amounts of hydronium and conjugate base.
but if what would they give us? What would they have to give us in order for us to make it 4x squared? I mean 4x cubed.
Yeah, so that would mean that one of the products here are going to be like when you multiply them. So that would mean like, let's just say one is x, and you said which one? 4x cubed.
Yep.
So the next thing after it being just 1x twice is 1x, and then something else. So like, okay, if I had something like this, over here.
Yeah, my question just like how many moles of the big like
Mhm.
whatever coordinate complex, like how many moles of that would we need in order for like if they were
Mhm.
would it be 2?
Yeah, so you would just see that reflected in the coefficient. Like up here, you see that, I mean, there's a coefficient in front of the water, but it's pure substance, so we don't use that. But if it said something like, yeah, let's say that it said something like, let's say 2 of this, or twice, the number of this kind of metal over here, that means that this compound here that has the metal must have a 2 in it as well. All right. But typically you're going to see that in balanced chemical reactions. That's basically something that they'll ask you for to answer in a context like this.
Okay.
Yeah. I could show you like an example of this. One sec. Oh, you know what? I just realized that oh my God, wait. I just realized that I actually solved this problem a couple of days ago. Oh God, I got it. Okay. All right, let me finally start to make some sense. Let me start. Okay, so we have yep. Okay, so we know this from the pH, and then the Ka would be the and then now each of so there's equivalent amounts of H plus and this aluminum hydroxide thing in the products. So I could just plug in 1 times 10 to the negative 3, 1 times 10 to the negative 3 over 0.1 because it's this one over here. And so this is going to give you 1e negative 6 over 1e negative 9. That's going to be 1e negative 6 minus negative 1 would give me 1 minus 6 or negative 5. And that's our Ka. And now the pKa would be negative log of 1 times 10 to the negative 5, which is just, 5, which is just 5 minus log of, minus log of 1, which is log of 1 is 0, so it's just 5. There you go. Yeah, I even wrote, I don't know if you could see this, but this is like, see how I was doing it like this? And then I just put a big cross through it.
Yeah.
So
Yeah.
that's what I was doing at first. And so you could see, I mean, oh, God, it's in reverse, but this is Henderson-Hasselbalch.
Mm.
So I was doing it that way too. And then I got,
Great minds think alike.
yeah. And then here, I'm just like,
Yeah.
thought about it in a different way, but yeah.
Okay, okay, okay. Okay, I hope that like on the exam I just wouldn't screw up in terms of the what you were saying with the like 4x cubed and 27x
Mm-hmm.
fourth power, but I guess they would make it like known with the moles. Anyways, I just don't want to waste too much time on this. There's
Sure.
different topic.
Yep.
So it was two problems. They're both enzyme kinetics related.
Okay.
I guess we could start with this. So the Michaelis, should I read it?
Yep.
Yeah. Okay. The Michaelis-Menten kinetic parameters were measured for enzyme E with substrate S, yielding a Km value of 2.5 millimolar and a Vmax of 100 nm per minute. If this first experiment were to be repeated with triple the concentration of enzyme, what would be the initial reaction velocity for the second trial when S equals 7.50 millimolar?
All right, tell me what your approach is.
So, when I understand the Km value is when it's when the Vmax is at its half.
Okay. So that's something similar. What else? What else is it about?
Um, well, the initial velocity. Um, one thing that's jumbled up in my head is like when exactly does Km equal S,
Yeah,
you
so
know?
so what you said first about KM is somewhat part of it, but specifically KM is itself, it's the substrate concentration at 1/2 Vmax.
Okay.
It's not 1/2 Vmax itself, it's the substrate concentration at 1/2 Vmax.
Yep. Okay.
So yep. And then let's see. So okay, we have so at 2.5 millimolar, what would the 1/2 Vmax be? It would be like the molar per minute over here, right?
Yeah.
Okay, cool. And then okay, so those are the values we have for Km and for Vmax. Now, if this experiment were to be repeated with triple the concentration of enzyme, what would be the initial reaction velocity for the second trial when S substrate concentration is 7.5 millimolar? So, okay. Well, we have triple the amount of the enzyme, and this specific value of 7.5 millimolar would be the substrate concentration, I guess, or not right away, but when they repeated that first experiment with triple the concentration of enzyme. So, okay, let's think about this, right? So if you triple the concentration of an enzyme, what could that be a part of?
Repeat that.
So if we had this triple the concentration of the enzyme, and then also they're tripling the substrate concentration too, right?
Okay.
So we want to know what would that V naught be for this situation where we now have um, triple the amount of enzyme and triple the amount of substrate.
Is V not the same as 1/2 Vmax?
Oh no, so like the start of Michaelis-Menten curve, I mean, would look like this with this dotted line as Vmax. And let's say this, or let's say this is Km, and then this would be 1/2 Vmax. Now, V naught is, if you were to zoom in like here,
Yeah.
you would see essentially a linear relationship, a straight line. And that's what V naught is. Essentially, it's the rate at which an enzyme can take a substrate and turn it into a product before it starts to flatten out near Vmax.
Okay. My original, like what I did originally is I literally just I divided 100 by 2 and I got 50. And then I saw that Km was 2.5 at 50. And I knew Km was concentration at half the Vmax. I just
Huh?
because 7.5 is 3 times 2.5. I just did 50 times 3 and I got 150, which was wrong. So that's why I was just confused, like what to do.
Got it. So let's see. Okay. I'm thinking about. Okay, there's a. Do you remember like the Michaelis-Menten kind of like formulas and stuff?
Somewhat. I know that Vmax equals V0, sorry, equals Vmax S over Km plus S.
Uh-huh. All right. Now, is there a way of expressing this using different terms? Maybe one of the terms being enzyme concentration.
Well, instead of um Vmax S,
Mhm.
Vmax S is 2 times. Actually, well, yeah. I don't know. I don't know.
So so Vmax is also equal to Kcat times enzyme concentration, and Kcat is the turnover rate, meaning essentially how many some amount of molecules per unit time that get converted from substrate to product. So that's another way to express Vmax. And we can kind of also see that it's proportional to the amount of enzyme concentration, right?
Yeah, but okay, yeah, so how does that relate though? Um,
Oh yeah, so that's okay. So yeah, that's the V. That's how you set up the V naught thing. But you could also see that if our Vmax is changing because what so okay, if the initial S substrate concentration for Km is 2.5 millimolar and the Vmax is 100 nanomolar per minute, when you triple the concentration of the enzyme, that's where we can see that here, if you triple this, it's proportional to Vmax. You should triple Vmax, right?
mhm.
So something that we can use is, or for this one, for this equation here, we can use this value over there. Um, so what could also help is why don't we figure out what the V max would be for that tripling kind of step?
300.
Good, because the V max they give us is the 100, blah blah blah, and then they don't really give us KCAT, but they do say that we're tripling the amount of enzyme. So yeah, we should have 300 whatever milli per min. So now what can we do here? Or maybe I can just plug in chug over here. So this would be the 300. This would be the 7.5 over Km. Isn't UKM going to be, I guess, okay. Yeah, I think it'll be the same. So 2.5 plus substrate concentration, which would be the 7.5 value. So this would be, I'll just do 3E2 times 8 over 2.5 plus 7.5 would be, I guess, like 3 or something. No, 10. And then 10, so this would be the 300 times 8 over 10. That goes into that. And then it's just 30 times 8, so 240. And yeah, I think that can work. That could be it right there.
That is it.
Okay.
Um,
Yeah, this is hard.
so yeah, but I mean, that's the thing. I'm asking you for like the hardest questions, I guess, just to see how you go through them. So, okay, what they expect us to know here is like even if we add the triple concentration of an enzyme, that's not gonna change the KM.
Mhm.
They want us to know that.
Okay.
Right?
Yeah. Yeah. So I guess, yeah, first I see that, okay, Km value of 2.5. So that's substrate concentration at 1/2 Vmax. And then they give me Vmax is 100 nanomolar per minute. So what would V naught be, in, yeah, like okay, that tells us, um, that we can solve for 1/2 Vmax if they asked us to, because it'll just be the 50. But then they say that they repeated it with triple the amount of concentration of the enzyme. Yep. So let's see. Yep. So yeah, I think the way, yeah. So the way that you did it was probably, a very probably intuitive way. It maybe like a higher percentage, chose that one. Um, but I think the main thing here is just understanding that, or would be kind of, I mean, yeah, I think it would be kind of just like this and this. And so they're giving us values for if you triple like the enzyme concentration as well as the substrate concentration. So you're going to just have triple the amount of, Vmax. And then that means you have a value, an actual value for Vmax. And you are also given the value of Km and the substrate concentration. And that's pretty much what we put together. And I would also say, like, just kind of look at, or kind of think of the things that can help a reaction proceed faster, like with what would produce a larger V. And that would be having like a high turnover number like this, or a high enzyme number like this, or a high, substrate concentration as well. But yeah, I think that's, yeah, it's just super. Oh yeah, so yeah, 41% shows that.
Interesting. Okay.
Yeah, but they probably just took the 7.5 thing and multiply it by like
Yeah.
100 or something like that. But yeah, tough here. So I would just make sure that you know these two formulas.
Yeah.
And oh, and then the thing that well, actually no, never mind. Yep, that's pretty much it.
Okay. Next is this, I guess, a little different. Because it takes into account mix and inhibition now. Compound I was identified as a novel allosteric inhibitor of enzyme X. The measured inhibitor dissociation constant Ki between the inhibitor and enzyme X was found to be 54 millimolar without any other substrate. With saturating amounts of non-reactive substrate analog, the measured Ki was found to be 76 micromolar. And then compound I is what?
All right. So when they say saturate, well, okay, yeah, just walk me through your thought process here.
Okay, I know a mix inhibitor is usually um it's usually when there's non-competitive inhibition.
Okay.
And so when there's non-competitive inhibition, we know for sure that the Vmax is reduced. But when you throw the word mixed inhibitor, either the Km can either be increased or decreased.
Yeah.
And if it binds to the actual site, like the main site, it increases Km. If it binds to the allosteric site,
Mhm.
it decreases the Km. That's what I remember. I don't know if it's right, but
Yeah. Um, so yeah, competitive inhibitors would bind to the enzyme's active site, and they will also look like the substrate. And that means that it would also it would increase Km, which means that it will require more substrate to reach Vmax from that shift in the curve to the right.
mhm.
So, and yeah, and then Vmax does not change. Um, something that can, something that you can do to reverse the effects of a competitive inhibitor is to just increase the amount of substrate. So in the question stem where it says saturating amounts of the substrate analog, that essentially means such a large amount, um, such that, oh, and then if it was a compound sorry, a competitive, I mean, inhibitor, yeah, you can overcome that with just increasing the substrate concentration. But yeah, pretty much that's what it does. And now non-competitive is going to bind to some allosteric site that is going to affect the shape of the enzyme. Um, and the Km does not change, but Vmax goes down because you're kind of blocking it from the enzyme from having stuff, having stuff be in the right shape for it to behave the way it does. And then uncompetitive would be when you start to bind only to the enzyme substrate complex, and that lowers Km and Vmax. And then mixed inhibition could be different for whatever type that we have, but we will be looking for changes in Km and Vmax. And so the question saying compound 1 was identified as a novel allosteric inhibitor. So right away we know that this would be maybe non-competitive or uncompetitive. Yep. So yeah, so now it's an allosteric inhibitor of enzyme X. The measured inhibitor dissociation constant, Ki, between the inhibitor and the enzyme X was found to be 54 micromolar without any substrate present. And then when you have saturating amounts of non-reactive substrate analog, um, the measured Ki was found to be 76 micromolar. So how could it be described compound 1? So if it's making the Ki go up, is that what you would think as you do this?
I just have a lot of things like okay, first of all, I think in terms of the Ki, when you have 76 Ki versus 54 Ki, from what I understand, like the lower the lower ki is the favored one.
Okay.
Right?
Yep.
So I guess without any substrate present, that's the free enzyme. So it favors the free enzyme, and so Km increases.
Yeah. So I think the Ki is like, the affinity for that the inhibitor has for the enzyme, whereas Km is the substrate concentration at 1/2 Vmax. So I guess we just want to look for what would be a relationship between Ki and Km.
A high value of dissociation constant corresponds to low affinity, correct?
You said high value of this association constant?
Of the Ki, of the dissociation constant,
Yeah.
right? So then the lower value means higher affinity. What I'm just a little confused about, honestly, is the difference between, because I just searched something up real quick, the difference between a substrate-free complex
Mm-hmm.
and, it's like the enzyme substrate complex, and then the substrate or the substrate-free or something, whatever.
Uh-huh. Yeah. So,
Yeah, free enzyme versus enzyme substrate. What's
oh,
the difference, basically?
so yeah, the free enzyme is just going to be that enzyme, I believe, right?
Without the substrate.
Yeah, yeah.
Okay.
So I think it's like so 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 competitive inhibitor or yeah, sorry, yeah, competitive will just be binding to the enzyme, not the enzyme substrate complex, but to the enzyme at the active site. Um, then uncompetitive will only bind the enzyme substrate complex. So uncompetitive is not binding to the free enzyme. Um, then you could have mixed, where it could be either an enzyme substrate complex or the enzyme. And non-competitive is having that as well. It can bind to either the enzyme substrate complex or to the enzyme. Essentially, kind of binding to the enzyme equally as much as it binds to the enzyme substrate complex. But that's pretty much what that is. And then the Ki value, so like Km would be like that dissociation constant for the substrate. Ki would be essentially the version of Km, but for the inhibitor. And if we see that the Ki is going up, that means that it's having a lower affinity for the enzyme. And then I guess we can go from there. So if it was non-competitive, okay, so like mixed could mean, I think, okay, so when I first read this, I was thinking about competitive because they said saturating amounts of non-reactive substrate analog. But I'm also thinking non-competitive because that's the one um that causes, well, not only causes the Km to increase, but that's the only one that would bind to that enzyme substrate um complex. Um so okay, so I'm thinking basically with some mixture of maybe a competitive and a non-competitive. Um that's what I would think here. Uh Okay, and then they just said that we have these different values. So, okay, if I look at a mixed inhibitor that results in a lower apparent Km relative to the uninhibited um, enzyme, and something that says same apparent Km, and then higher Km, and then D just says purely non-competitive. That only lowers the apparent Vmax relative to the uninhibited enzyme. But if it's mixed, it can't be purely non-competitive, right?
Yeah.
So I would get rid of that, and then if I'm treating the Km exactly as the Ki, that would mean that I would have a higher, well, yeah, a higher Km, right?
That's what I was thinking. Okay.
Yeah.
All right. Okay.
Yep.
I'd rather keep moving along.
Yep.
Um, the thing is, so like these are bio passages. Well, there's only one more I wanted to go over. We just have 40 minutes, so maybe I guess if we could try to like go through it fast.
Okay. Seems like it's quite a lot of stuff, but yeah, we can try our best.
Yeah.
Yep. So we can do it. Let's aim to read it, finish it by like maybe 4 minutes.
Mm-hmm.
Okay.
Okay. Dystroglycan, the transmembrane protein that mediates interactions between cytoskeleton and the extracellular matrix. Actually, you know what I'm thinking? It might be more worth it to do this passage just shorter.
Okay.
Yeah.
Oh, and
Um,
did you get wrong for this?
what's up?
Oh, how many did you get wrong for this?
A good amount. A good amount. I just forget how many. I think like everything except one.
Okay. Got it.
Yeah. Okay. Yeah, it's just still less things. So, apolipoprotein is an important protein of primate innate immunity, particularly against trypanosome infection. Should I stop after each sentence or
If you see certain buzzwords, which
right?
yeah.
I don't see a buzzword.
Oh yeah. So you know what? I'll do the
Okay.
so I mean we have innate immunity,
Mm-hmm.
43 kilodaltons. Like they could ask you how many amino acids does this thing have, right? And then you'd use 110 daltons per amino acid, right?
Yep. Yep.
Yep. You can continue.
Okay. Apol is a 43 kilodalton protein that is secreted mainly for hepatocytes as a component of high certain HDL particles that also contain targeting proteins that bind to trypanosomes and induce endocytosis of the HDL particle. Um, okay. I mean, HDL maybe is a buzzword.
Mm-hmm. Yep. And then um endocytosis of the HDL particle. But yeah.
Mm-hmm. Acidification of the trypanosomal endosome induces APOL1 to transfer from the aqueous lumen to integrate into the endosomal membrane, forming a closed ion channel. Um, aqueous maybe.
Okay.
Uh, as the endosomal membrane is recycled back into the plasma membrane, the pH neutralization of the cis side, um, which is the luminal side of endosome's extracellular side of the plasma membrane, then activates the ion channel, allowing sodium and potassium cations to flow through. Um, I'll just finish it.
Okay.
In other words, APOL1 acts as a ligand-gated ion channel that opens when its ligand H plus unbinds. And depolarization, dysregulation of ion flux then leads to osmotic lysis of the trypanosome parasite.
Okay.
All right. So something we should probably highlight ion channel. pH neutralization is cis side. So like when it tells us the cis side, where it says luminal side and endosomes, extracellular side.
So it seems like they're saying that one of I guess acidification as well. Yeah, if they acidify this trypanosomal endosome, that causes APOL1 to transfer from, and then APOL1 is that 43 kilodalton protein. That plays a role in immunity. So okay. Transfer from the aqueous lumen to integrate into the endosomal membrane, forming a closed ion channel. All right, as the endosomal membrane is recycled back into the plasma membrane, pH neutralization of the cis side then activates the ion channel that lets sodium potassium kind of flow. Then, in other words, okay, APOL1 acts as a ligand-gated ion channel, opens when H plus or its ligand H plus no longer binds to it. And then due to depolarization of and dysregulation of the ion flux, causes the trypanosome parasite to burst or whatever. Okay.
To structurally characterize the topology of the APOL1 ion channel, researchers used bioinformatics methods based on the APOL1 primary sequence to predict transmembrane regions, as well as an experimental technique called substituted cysteine accessibility method SCAM to determine extracellular and intracellular localization of intervening loops. To perform SCAM, the researchers substituted specific amino acids in these loops with cysteine residues, allowed the APOL1 mutants to form functional ion channels.
So let's see.
Yeah.
So we're talking about the structure of APOL1. And they used bioinformatics, which I'm surprised to see on this test, but that's pretty cool. Based on APOL1 primary sequence to predict transmembrane regions in this method called SCAM, which is funny.
Yep.
And anytime you see transmembrane, just think, okay, non-polar amino acids.
Okay. What is the opposite of transmembrane?
I guess, it'll be polar, so it'll be something if on the inside of the cell or
Mhm.
something on the outside. Whereas the bilayer itself is the fat soluble one.
Okay. A 53 kilodalton, sorry. To perform SCAM, researchers substituted specific amino acids in these loops with cysteine residues, allowed APOL mutants to form functional ion channels. 53 kilodalton thiol reactive reagent. MPBS was then added to the cis face, extracellular side of the channels. And the molecular weight of the APOL1 complex was added, analyzed by non-reducing SCS page, followed by a Western blot. Okay.
All right, right away, I can see something that they might ask, which is related to the non-reducing SDS page. What are you thinking of?
Like they could ask about disulfide interactions, but
The-
non-reducing SCS page doesn't remove the thiol groups.
Yep, exactly. Good. Perfect. So, all right. Yep. And then you can. Oh, yeah. I guess now it's just the figure. So, Western blots of APOL reacted with A MPBS, B MPBS without streptopvidin, and then MPBS with 1% weight by volume, maybe W over V, DDM, which is that that other thing at the bottom, very bottom. All right then. So, yeah, okay. A lot of stuff happening here. Let's try our best.
So question 13, I just want to skip it. Like I just skipped something while I was reading it originally. It asked for like the protein structure, and I didn't see primary sequence, so I know primary is only hydrogen bonds. Oh, wait, no, peptide bonds. Sorry, peptide bonds. Secondary is hydrogen, right?
Yeah, secondary would be hydrogen
Yes.
bonding between
Yes,
the
yes, yes.
backbone.
Yes. I just missed it while I was reading it because you highlighted it. They said APOL1 primary sequence, and
Mhm.
that's about the studies. I just want to skip that.
Yeah.
Yes, we can start here.
I knew they're gonna ask this. I even drew it. Something like
Yep, yep.
with the this is the transmembrane, but they love asking questions like this. Like it's almost pretty much guaranteed. Like anytime you see transmembrane, like they're gonna likely ask you.
Mm-hmm.
Okay.
Okay, so they're asking something that's going from polar to non-polar, right?
Uh, let's see. Inclusion of which amino acid is most likely responsible for the changing localization, soluble luminal to integral membrane of okay, APOL1 during pH manipulation. So what's causing it to go from where it is, I think, inside of the cell to it being an integral protein or integral membrane, which I think means similarly, like similar to the transmembrane.
Right.
We could also kind of use somewhat of a process of elimination because which one is like the most different here?
Um, Isoleucine.
Yep. And if they're saying that the integral membrane, or if the integral membrane is a transmembrane, then yeah, I would say that it would have to be the one that's not charged.
Nope.
Oh, damn it. Okay.
Um,
Yep.
yeah.
Changing localization from the lumen to the integral membrane. All right, let's see what these guys say. Neutral apol is luminal. Then the transmembrane part with okay. I see. They told us about um acidification here. That's it right there.
Right.
Yeah. If you go back to this question stem, so they're saying upon pH manipulation, which means the experimenters are altering the pH to learn more about this. And that's what they say right there in that second paragraph, that acidification, aka manipulating the pH, uh, causes the APOL1 to transfer from that aqueous lumen to integrate into the actual membrane or the endosomal membrane to form that closed ion channel. So let's see, hydrophobic inclusion would be at low p, or it would not be stable in the aqueous lumen at neutral.
But where do you see that it's pH neutralization? So we needed to know that. So what we needed to know that like it goes from neutral pH of 7 to like a super acidic pH. Because like okay.
Okay, I
'Cause-
think I also yeah, sorry, what were you gonna say?
no, I was just thinking because the pK of like the side chain of glutamate, I mean it would be a pretty low pKa, right? But like
Mhm.
I guess what if the pH drops um okay. Yeah, whatever.
Yeah, so here, so we know that glutamate is an acidic amino acid that changes its protonation state at different pHs. At neutral pH, the glutamate side chain is negatively charged and therefore highly soluble. When the pH drops, aka the acidification part, glutamate, surprise, like itself becomes protonated because we're it's choosing a pH that's going to be lower than its pKa. So that will neutralize the charge and make it less water soluble, therefore um more like fat soluble. So that's something that happens with glutamate because so we want to essentially ask ourselves if the pH drops, what amino acid would be the most affected by that? Now, it could be things that now for this pH dropping, I should say that the range is like between 7 and then like lower than 7. But uh so if it goes down lower than 7, it will be something like glutamate, which has that kind of charge in that kind of environment. Whereas histidine and lysine would be, well, would have pKa's that are higher than that of like the water. So the histidine and lysine wouldn't like neutralize something. We essentially want to figure out which amino acid is the most can change the most when you change pH, and glutamate would be something that could be that, um, which is kind of weird. But over here in the picture, yeah. So here we have at neutral pH, it has a charge, but for an acidic pH, it can make itself part of that transmembrane domain.
Why? But that's the part I
Yep.
didn't fully get. I mean, because it's neutral that I thought the things in the membrane are hydrophobic, non-polar.
Yeah. So if you took the inside of this and you lowered the pH, meaning, so I guess what's confusing here is that when we read acidification, we think of it as being the glutamate or acidic amino acid, but what they really mean is that when you drop the pH of the environment, what would happen to the glutamate? Well, if we get the pH to drop, as we get the pH to drop, like it'll behave more uh like the glutamate will behave more as a base to get these protonated due to the drop in pH of that environment that it's in. So we want to ask ourselves, if we drop the pH, how would that affect, the charge of either an acidic or a basic amino acid? So if it was something like, yeah,
Okay, so like if it was histidine, histidine is basic. Um, so what? At neutral, it's has a positive charge, right?
histidine's like the one exception where although it's basic, or we call, we say it's basic, its side chain is actually has a pKa of 6, which is below that of physiological pH. So histidine, you'll kind of see sometimes histidine having no net charge at physiological pH.
Okay, I'm gonna be honest. We have 18 minutes. Let's just, try to get through as many of these as possible. I do more or less get what
Yeah.
they're saying. It was just a little tricky.
It's very.
Um, yeah.
Mhm.
Okay, here's one that I feel like is will be really helpful to go over because it's just like applicable to so many problems. So it asks what was the purpose of NBP without streptavidin and then experiment. What was the purpose of it? NBPS and detergent. And so it's basically asking which one is positive control, which one is a negative control.
Yeah.
Um, and so it's referring to these studies. So study B and study C. Where study B is the one without streptavidin, and then study C is the one with the detergent.
Okay.
My understanding is that a positive control versus a negative control. With the positive control, you know for sure that you're gonna have something happen. You're gonna have a reaction, I guess, or like there's gonna be an effect.
Okay.
And a negative control has no effect. Like nothing happens, right?
Yeah. Yeah. So, uh, yeah. Okay. So the MPB thing was this experiment was repeated with. Well, first I'll look at MPBS. The okay, thiol reactive reagent is the MPBS, and then the MPB is something. What did I say MPB was?
Yeah, yeah. Right here, MPB without streptavidin.
Yeah. So I guess it doesn't tell us what that.
No.
All right, let's see. MPB. Oh, I didn't even look at like the actual plots here. Maybe I don't have to. Or maybe they'll ask. Okay, never mind. So let's see. Did you use this figure to answer this?
Yes, I did.
Okay. All right, tell me what how you answered it.
Okay, I got it wrong, obviously. My original understanding was like with MBP without streptavidin, which is B.
Okay.
In here, it's showing a react, like something happens, they move. That's what I thought. Um, while in C, nothing happened. Like none of the uh samples moved. And so I thought that it was A. I thought because there was a reaction or whatever, like MVP without streptomycin had an effect. So I put that as positive control, but I'm pretty sure it was wrong.
Okay. So I see that. Okay. Okay. So MPBS and detergent is DD. No. Oh, it is DDM.
Yep.
Oh, wait. Okay, I think that the MPB without streptavidin, I think that would be the negative control because, well, I have everything moving here, and here I have everything or one thing moving down, and then A, it's just, well, the wild type seems to just have this KD.
Yeah.
And we have two that, so this moves forward, here everything moves forward, and here only this moves forward. So here we're expecting to see perhaps that the MPB, or sorry, the wild type being the one that survives. That I think could be the okay. So trying to think which one would be positive, which one's negative, and I think did you get something like or think something similar to that? I'm like looking through the passage to see if there's anything else that I miss.
Well, I got it wrong. Like, yeah, B is a negative. I just didn't understand why, because there's a reaction. In B, there's a reaction though. I just don't get that.
Oh, did you get, is that B?
That's the correct answer. Yeah, yeah, yeah.
Okay, got it. So, okay. Experiment. So for positive control, APOL1 always binds MPBS and changes molecular weight. Okay. APOL1 molecular weight is primarily or minimally affected, regardless. Okay. Let's go down a little bit more. All right, so okay, size seems to be playing a role here. Let's see. MPV, okay. Okay. It seems like the biggest thing here is the size. And if we had APOL1 with a 40 kilodalton protein, and then we have 53 kilodalton for the version of it with the MPBS over here. 1, 2, 3. And this one. Okay. Yeah. So I think that they're just kind of having you look for how the size of something plays a role. And in the example where we have everything moving, or in the example where we just have one moving, I think that, okay. Now they also said that the cis, or sorry, they labeled something with cysteine. All right, I think I'm just gonna take a screenshot and I'm gonna like work on this outside of our session just because,
I appreciate it.
yeah, I feel like I need to like actually read it properly because I'm not remembering what I see in the oops. Yeah, I'm gonna like, yeah, after our session, I'm just gonna like take us like go over it more slowly because I'm seeing things that I'm trying to like fit into my head, and I just noticed that the weights play a large role. But yeah, I'll try to do this on my own time. But sorry, I can't like get it right away.
Appreciate it. Don't even worry. Thank you.
Yep.
I guess the last question we could go over today, it's this, and it kind of connects two concepts of our session.
Got it.
So the cysteine MBPS reaction is a redox reaction involving nucleophilic attack of MBPS by a deprotonated cysteine side chain. If the reaction was attempted at pH 7, what percent of the cysteine side chains would be in the deprotonated anionic form? And it tells us cysteine side chains have a pK of 8.
Okay, so we seem to have MPBS, which was the protein thing. Thiol reactive agent. Okay. Nucleophilic attack on MPBS by a deprotonated cysteine side chain. If the reaction were attempted at pH of 7, approximately what percent of cysteine side chains would be in the deprotonated anionic form? So we can do, I think for this one, let me make sure. So we have, okay, percentage. You know what? This might be something that Henderson-Hasselbalch might help with. See that 7 is equal to 8 plus log of and -1. And then if, okay, we want to see what percent of HA turns into A minus. And from here, we can actually do 10 to the power of -1 is equal to A minus over HA. And so that would mean, like, well, this is 1E minus, oops, -1. So, and that's the same thing as 0.1. So if this is 0.1, that's 10, yeah, that's 0.1, which is this ratio here. So 0.1% or 10% of the thing, of the enzyme, is going to be deprotonated. I think so. I hope so. All right.
You're right.
So,
But why'd you think right away Henderson-Hasselbalch? Because you saw pH and pKa?
Yeah, that's a good question. Yeah, I think when I saw those two, and according like compared to the previous ones that we did today, where they didn't really give us a pKa value, but this one, this question stem does. So yeah, so I chose to use that. But that was a good question.
Right. Okay. Um, all right.
Hmm.
I think, I mean, that's all. Um,
Yeah.
I guess there was this. We have like 2, 3 minutes. I won't even go over it, but like, yeah, we could probably just end it here.